And next, we are going to be going to some esoteric territory, a little heavy for the afternoon, but very interesting. And that's going to be a panel on quantum technology. And with that, we have Yuri Anderson, co-founder of New Quantum, and Rossi Nguyen Nguyen, senior product manager at Riverlane, again joining us online. Hello and welcome, Yuri and Rossi. Welcome.
Hello.
We can all hear one another.
Hello, everyone.
Perfect. Okay, now, firstly, we are entering mind-blowing territory, even more so because in Singapore it's in the afternoon. Now, mind-blowing because, let's be honest, when we think of quantum tech, most of us don't know what it means. We can't wrap our heads around it. But secondly, mind-blowing because it is going to significantly change the way we live, work, and play. So help us out here. For starters, let's ask the same question to both of you. Yuri, can you help us break it down into layman terms? What is quantum technology? And I would like you to explain it so a 10-year-old kid can understand.
I will certainly try. So quantum technology is really about controlling matter on the very, very smallest level. So we're talking subatomic level. For example, you're talking about electrons that spin around an atom, for example. And it turns out when you are dealing with matter on that level, on that very microscopic level, you're starting to get some phenomena that you don't see in the macroscopic world. But it turns out that we can describe this very well. And this is a science that's been well known for over 100 years. And we can describe it very well with mathematics. And what we're trying to do now is to sort of reverse that. Now that we understand mathematics, we're trying to control the matter in such a way that we can do useful things like computation and sensing and detecting and communications.
Yuri, this 10-year-old must be really, really smart. Well, can we give an example that even a 10-year-old might understand? What is quantum tech in a few lines? I know it's tough. It's
there's many aspects. Sorry, and I think we'll talk a little bit about the different aspects of quantum, but it involves things like sensing. So you have things like single photon detection, which means that you can detect single particles of light. Which means that you can do very, very sensitive measurements. You can also use those particles of light to communicate securely. So you have an exchange of security encryption keys using photons. And of course you have computing, which is a whole topic to itself, and all kinds of wonderful things you can do.
So as far as the 10-year-old is concerned, with quantum tech, he can now make sure his or her messages are not read by the mom or dad. So that's probably what they care about, perhaps, more secure.
Exactly
now, Rossi,
that.
You saw Yuri sweat. That was a tough question. Same difficult question for you, except what is quantum tech as described to an 80-year-old grandma?
Oh, wow. 80-year-old grandma. So if I have to explain quantum tech to my grandma, I assume she would not know computers. So probably talking about computers is not going to help.
They would. I think 80-year-old, they know computers, but very basic.
Okay. Well, we can try with something that's more regular object. So I will ask my grandma to think about her, let's say, a living room light switch that can turn on and off. Mm-hmm. So when you flip this switch, the light either turn on or off. There's no in between. But in the quantum world, like Yuri mentions, the world of very small particles, like atoms or subatomic level, like electron or photons, it's like having this light switch. You can switch it on and off, but you can also kind of put it in a superposition state, which is, it's kind of like between on and off. Mm-hmm. It's like a dimmable light, but now we're talking about a regular light switch. This phenomena is possible because in this very small world, these particles can exist in multiple states simultaneously. And so that is superposition state of in the quantum world. There's another also very spooky and weird property in this quantum world. is that we call something called entanglement. That's when you put these two particles together, you can link them together and you can take one and send them off far away and somehow they communicate with each other.
And we'll get there because it's almost getting into teleportation of information without them physically having to interact. But I wanted to go back to your analogy of that light switch because I thought it was a very easy to understand one. So imagine now, Grandma, instead of a switch that is either fully on, too bright, or fully off, too dark, now there are infinite gradients in between, right? Very slightly dim to kind of bright, but not too bright, right? Along the entire spectrum. Okay, so I hope that we haven't lost most of our audience. We're almost there, yes? It also means for those of you that are bettors, lottery, instead of heads or tails, now you can use quantum computing or technologies to use superpositions, right, to maximize your winning. 97% of the time, I've been told, right? So great way for us to know. Okay, but we'll debate that later. Okay, so great. We're a little clear on what quantum tech is. And now, again, Yuri, you were talking about quantum technology broken into three commonly spoken categories: quantum imaging and sensing, communications, and of course, quantum computing. Help us out. Describe for us first, what is quantum imaging and sensing? How is it being used? And how ready is this to be used today?
Yeah, absolutely. So quantum sensing is fundamental. It's fundamental to everything within quantum. So it's a technology that's used both for communications and also for computing. But it actually has applications on its own as well, and that's really interesting to see that there's a lot of technologies now that are maturing to the point where you're seeing industrial applications. I can give one example. I've been working and co-founded a company called QLM Technologies that build gas sensing cameras. So these are used for detecting methane emissions, CO2 emissions as well. So it's very useful. And the reason why those cameras are particularly good is because they use single photon detection. And I talked about those particles of light. When you can measure things on that level of granularity, on that level of detail, you can also make very, very detailed measurements of things that objects that you want to measure. For example, a gas cloud, so you can image how much gas is being emitted, where it's being emitted, and you can build a whole new generation of cameras that really help in terms of sustainability. This is all about getting emissions under control, for example. So that's one real life example of sensing technology and imaging technology that's ready today.
And really getting, like you said, to the subatomic level of detecting these emissions like methane and be able to do more precise tracking. So that was quantum imaging and sensing. What about for quantum communications? Something you briefly touched on. Can you expand on it?
Yeah, absolutely. So as you mentioned, people want to send data encrypted and securely, whether it's a teenager sending stuff that they don't want their parents to know about, or if it's government sending sensitive information to their embassies or whatever it might be. So when you require that higher level of security, then quantum communications can provide a solution. The two sides of quantum computing is that it can do a lot of wonderful things, and I think Rossi will tell us a lot more about what her company are doing. But one thing that we know that quantum computers can also do is to break current encryption. So anything that's today used, and most of the encryption that's used today will be able to be broken by a quantum computer. So that means we need to have countermeasures because we still want to be able to secure communication. And this is where quantum key distribution, for example, comes into play. And that's using the properties of photons, these particles of light, because if somebody tries to intercept them, you will detect that. You cannot copy information in the way that you can with classical information. So QKD, quantum key distribution, offers a way to securely exchange keys.
Mm-hmm. So it really sounds like basically everybody today, all of our very securely encrypted devices, any of them can be broken by a quantum computer, but then you just have to, in the future, use a quantum computer. So it'll be unbreakable encryption. Very interesting. And I think that's very pertinent because I read a stat somewhere that today alone we have 40 billion connected devices. So it's all the more critical that we have unbreakable encryption. And now let's go to
Absolutely.
Rossi. Rossi, you work a lot in quantum computing. What is this whole hype about quantum computing? Help us understand it and how it's being used.
Yeah, I mean, it is indeed a hype, but I think it's also the underlying technology itself is also incredible. I think we talk about quantum computer is the new generations of computer that use this quirky and weird, strange phenomena of quantum mechanics, the one that we just explained, superposition, entanglement. We use these phenomena to actually encode informations differently than we do in classical computers. And so we want to use the quantum computer to harness the advantage of quantum mechanics and doing, more faster, more complex calculations, like breaking encryption, like Yuri mentions. So yeah, that's the gist of quantum computing.
So, again, I did my own research on this topic to just wrap my head around it. And I heard that even though we are talking about it being faster, much faster, actually, I've heard that basically a quantum computer is no more a better computer. It's not fair to call it a better computer, just as it's not fair to say that the light bulb is a better candle, if that makes sense.
Mm-hmm.
The light bulb is not
Yes.
a better candle. So similarly, the quantum computer is not just a better computer. It's not a fair comparison. So how should we really start thinking about this and its potential?
Good questions. So I think that's why I said it's the next generations of computing device, because if you talk about faster computer, you will think about high performance computing computers. We already have nowadays classical computer. You can have more computing power fast and you can compute faster, but quantum computer can solve some problem that is, you need to encode in much more complex space. It's not only faster, but it's also more, the complexity of the problem that you can solve. So I can take an example
What
of
about
some
healthcare?
simulations.
We've heard about mapping of molecules in healthcare, coming up with new drugs, pharmaceutical drugs. Would that be something you can elaborate on?
Yeah, so I like this example of a coffee molecule. I'm not an expert in this field, but this is, so knowing quantum computer, you will think about it has the ability to simulate and model certain molecule. So coffee molecule, we probably all of us drink coffee, but up to today, we don't have a proper computer that it can properly simulate this coffee molecule. And it's very simple molecule and very common nowadays. So imagine the future that we can actually understand at this level molecule and what we can do with these computers. The same way we don't expect to call through via Teams now using computer, the actual calculator of like 100 years ago.
Absolutely. So there's just so much more beyond speed. But since we did touch on speed, just give us a sense of how much faster quantum computers are. That's 158 million times faster than the most sophisticated supercomputer today. What it really means is that it can do in 4 minutes what your standard supercomputer would take 10,000 years to complete. 4 minutes versus 10,000 years. That's just how fast we're talking about purely from speed alone. But as we've heard, quantum is so much more than just about speed. So let's plow on a little bit more. Rossi and Yuri, maybe starting from Yuri first this time. What are some of the other major breakthroughs in quantum technology that you are personally very excited about? And pitch to us, why should we care about it as well?
Well, I think I mentioned one thing already, which was the sensing and the ability to see things that other conventional cameras cannot see and on that resolution, and that translates to a lot of other sensing applications as well. People are looking at more precise gravitometers, for example, that they can put on satellites. Still a few years out, but those kind of things can give us very, very precise measurements. It can give us very precise timing and things like that. So it's just improvements on all those levels, I think, that will be woven into the fabric of everyday life. I mean, ultimately, we want to get to a point where we don't even talk about computing, quantum. It's just part of the fabric where that makes its way into everyday products and everyday services. And we're starting to get there with some of the things that we're looking at the moment. I think obviously computing is the big exciting the real game changer here, but everything else around it is exciting too in terms of communications and sensing.
Absolutely, and especially when it comes to sensing, the precision for detection, we'll come back to that, especially when we talk about mobility applications and potential. Rossi, what else are you excited about in terms of breakthroughs in quantum, and why should we be excited too?
I think I can be very biased here because I work in specific field in quantum. It's called quantum error corrections. So if you might have heard of in 2019 when Google team claimed that they achieved quantum supremacy, referring to the fact that a quantum computer can perform a task that is not possible in a normal computer. So they perform this task that take 200 seconds instead of 1,000 of years to compute if you use a classical computer. So that is a great breakthrough. But just to demyth the hype, that quantum computer nowadays is still very noisy. So one of the biggest challenge in quantum computing is dealing with these errors that occur because of environmental noise or imperfect hardware. So, but in like 20 years ago, in mid-90s, scientists came up with the theory of quantum error corrections. It's a clever way that you can protect the quantum information by encoding them in special way. And back then it was very much a fantasy of theorists. You don't have technology to test on, but in 10, 20 years time, so now fast forward to today, the idea of quantum error correction is no longer just, in theory, we actually can implement it, and we actually experience the advantage of quantum error corrections. And this coined term is very important in quantum computing field, the term of fault-tolerant quantum computer. It's a the generation of quantum computer that can be protected from the environmental noise and is equipped with quantum error correction protocol.
Right, so you are working on quantum error correction, and one of the big things you're working on is also reducing the noise that comes from quantum computers. Can we get some questions from our guests here at MBS or online? I hope we've tried to make quantum as accessible as possible so far. It's tough, that's why they're all PhDs. Yes, one of our startup founders, Dr. Ali, takes a PhD to ask this esoteric questions. Please, Dr. Ali.
Thank you. So since we have been talking about mobility, so what are the few use cases of quantum computing that we are going to see for mobility use cases? So if the speakers can elaborate on that.
Right, use cases of phonic computing. Yes?
Yes,
Okay.
for mobility. Yeah, for autonomous mobility or the next generation of mobility.
Okay, so use cases of phonic computers, quantum computers, as is applied to next-gen mobility solutions. I'm just doing a quick tech check if our speakers are still online with us or have they dropped off because of technical challenges. So let's give them a few seconds. I'm noting down your question. So application of phonic computers as it applies to mobility. Other questions? Let's collect some questions and we will load them onto our speakers when they come back online. Any other questions? Any clarifications? I'm sure that their explanations has generated more interest and follow-on questions. Are you convinced that we need quantum computers? Are we clear about how they might change the way we work, live, and play? If not, this is your chance. We don't often get to be in the presence of quantum experts. Yes, gentleman at the back.
Hi, I'm Yongshin from Continental Automotive. Right, so this in relation to one of the remarks that Rosie has mentioned, because currently we are still in the noisy intermediate scale quantum computing era. That's why we need error correction to maintain the integrity of the quantum computations. Right, so in between noisy intermediate scale era and to a fully fault tolerant quantum computing. So I would like to ask for their opinions, like how far are we to reach that?
So how far are we from fault-free quantum computing? Well, that's a tough question. And again, that actually marks the end of all of our exciting fireside panels.